I'm Anil Kumar. Welcome to my series on advanced calculus. Here is a very important topic for which I've got many requests. Students working for IIT JEE will also benefit from this particular video. We'll talk about approximations and errors, and we are going to estimate values using differentials. So the topic, differentials, errors, and approximations. Well, some of you also treat them as uncertainties. So we will have talk about uncertainties in checking the values, right? That's what it means. So let us see how these errors arise. So let me first provide you with a geometric view of what we are trying to approach here. We'll actually have mathematical model and some basic terms we'll define using absolute error, relative error, percentage errors, and we'll have a few examples where we are going to calculate the square root of numbers and then estimate them, right? And we'll also find percentage errors in calculations. So let me begin with a very simple graph. We'll take kind of a parabola, right? It's kind of easier to explain with the help of a parabolic path since it's kind of increasing all the way. So we'll take that function. So as you have understood that when we talk about derivatives, we are actually approximating a secant. So let me draw a secant here. Secant is any line which goes through 2 points. So let me just draw a secant here. Let's say that is the secant for us. Okay. So it goes from 2 points. Let's call these points as P and Q. So we'll call this point as P and the other point as Q. Now the idea of tangent is to bring this point Q very, very close to P, right? So that we get a secant which approaches a tangent. So let's say this point here gives you the value of X and Y, right? Now the idea is to get a point Q which is very close to P. So we'll say delta X away, right? So this position is delta X away horizontally, and so vertically the value will be f of X plus delta X, correct? So that is the Y value. Now as you bring Q point very close to P, we get a tangent. So let me sketch a tangent here. So let's say this is the tangent for us. So this tangent we refer by dy dx at a point this P, correct? That's the tangent. Now whenever we are approximating things, what we really do is that we find a point which is this point on the tangent. So we call this point as dy. And the earlier point was actually the change in Y value. So do you see these two are very different from one another? So that causes an error. So I hope you have understood the source of error. Source of error is because we are working on the approximation, right? So that is why we get this source of error. Correct? So I hope this geometry is very clear to you, right? So what we're trying to say here is that whenever we are talking about change in Y over change in X, that is basically slope of secant, right? And as delta X approaches 0, delta Y over delta X approaches dy dx. Right? So it approaches, it is not exactly there, right? And you can clearly see there is always a difference, perfect, since we cannot have just one point. So there is a separation. So dy is this point which we are normally talking about, and delta y is that big point. So delta y over dx is kind of different. However, what you notice here is that dx and delta x are kind of same. So for our calculations, dx is equal to delta x. Right? This is very important to understand. Correct? So that is the geometry part of what we were trying to think about, right? Now let's look into the mathematical model. So mathematically, we are saying that the y value for the function is basically f of x plus delta x, correct? This is what we are trying to say, right? So we know that y plus delta y is approximated, or we write this as f of x plus delta x, correct? So the original value of y, so this is y, right? Y plus delta y actually is the value of f of x plus delta x, right? So this value here is f of x plus delta x, right? So that point is very clear. That is this point Q which we are talking about, correct? Now what you also saw here is that delta y over delta x is approximated as dy by dx, correct? That is how we approximate, right? So combining these two, we can say f of x plus delta x, which is equals to y plus delta y. Now in this particular case, as you can see, if we have delta y from here, let me just draw a line here. We'll extend this part. Okay, so what we are trying to write here is that delta y is basically equal to, and that is the approximation which we are trying to say, is dy dx times delta x. Do you see that part? So from here we get to this step, and when we say dy dx, we are actually saying derivative, right? Or you could also write derivative of x times delta x. That is what we are trying to say, right? So that causes the approximation. So we can write this as equal to y plus dy dx times delta x, correct? So that is where the approximation comes. So we just say that x plus delta x is actually equals to y plus dy dx dot delta x, correct? So this is the geometry which you just saw. Perfect. Now let's try to create our model. So model will be, we know this creates an error, and that's why we wrote approximately equal to. Right. So in a way, we can see that the limit when x delta x approaches, I should say, approaches 0 for delta y over delta x, in that case it is exactly equal to dy over dx, right? Only when delta x is approaching 0, right? So, or you could write this as f dash x. So here no approximation. Correct? So in this case there is no approximation. But when we use, well, actually delta x cannot be exactly 0. It is very close to 0, right? Therefore, we could also write this as delta y over delta x is basically equal to this derivative plus some error, e. So this error, where e approaches 0 if or when x approaches 0, right? Delta x approaches 0. So that is where e approaches 0, as I should say delta x approaches 0, right? So that is how they are kind of related. So the exact value of delta y is basically equal to f dash x times delta x plus e times delta x, correct? So we'll just multiply with delta x, correct? So that is the exact value. Perfect. However, the approximate value is, we just forget about this error, right? So we can write delta y equals to f dash x or dy dx times delta x, right? So this, or we can write this as dy dx times delta x. So this is the approximate value. since we forgot this, or we kind of excluded it, because since this is very, very small. So that is what we normally work with, right? So only the first factor. We normally forget about this. And that causes approximations and errors. Perfect? That is what is the error is. Now, let's try to define some of the terms before I move to the next page and talk about few examples. So we say that there is a relative error. Then the relative error is, or we can begin with the absolute error in delta x itself, right? So we have a couple of errors. One we call as absolute error. In this case, absolute error is the change, delta x itself, error in delta x, right? That is the absolute error. Relative error is when we are comparing it with its original value, x, right? So that ratio is the relative error. And percent error is when this is multiplied by 100. So when I say there is 1% error in the independent variable x, it means delta x over x times 100. That's what it means, right? So if I say 1% error, 1% error in independent variable, in that case, it means delta x over x times 100 is equal to 1%. That is what it means. Perfect. So I hope you got a gist of the mathematical terms. And now let's take a few examples that will help you to understand the whole concept. Perfect. So the question for us is question number 1. If y equals to 3x squared minus 6 and if x changes from 2 to 2.1, find the approximate change in y, changed value of y, and percent change in y. Right? So that's the question for you. You can pause the video and answer this question. When we say that the change is from 2 to 2.1%, that means we're talking about a 5% change in the input, right? From 2 to 2.1. 10% would be 0.2. Perfect. So we are given the function as y equals to 3x squared minus 6. Now at x equals to 2, y value is equals to 3 times 2 squared minus 6, which is equal to 3 times 4 minus 6, or 12 minus 6, which is 6, right? So it is 6. So the value of y at 2 is 6. Now we need to actually figure out what is the approximate change in y. So how do you find change in y? So from the concept which we just learned, we can find the derivative of this function with respect to x. So we get dy dx as equal to 6x, right? So that's the derivative with respect to x. Now, if the value is at 2, then the derivative at x equals to 2 is going to be 6 times 2, which is equal to, so we get derivative or rate of change at x equals to 2 is equal to 12, correct? So that is dy dx, which is at this. So from here, what do you get? When you are making a change, that is the delta x is changing from 2 to 2.1. So what is delta x? So delta x in this is 0.1, right? So the change delta x is basically equal to 2.1 minus 2, which is 0.1. So that is the change, right? So from here, we can say dy is basically equal to, in our function, dy is equal to dy dx times delta x, correct? So dy dx is at x equals to 2, which we just found here, dy dx at x equals to 2, right? So we get dy, change in y, basically is equal to 12 times 0.1 or 1.2. So that is the. So from here we know that the change in y, we should actually write delta y instead of dy. Change in y is 1.2. So the answer for the first part is approximate change in y is equal to 1.2, right? So I should use delta y here basically. Okay. The second part is changed value of y. So the changed value, this is A now, and for B, which is changed value of y, that means the value of y plus this value, correct? Because that was at the value at 2. So changed value of y, so that means the value, changed value will be original value, which is 6 for us at x equals to 2 plus 1.2, which gives us 7.2. Is that okay? And part C is percentage change in y. So percentage change basically is, let me write down here. Let me write down the formula for percent change and then we'll calculate. Equals to change over original value times 100. So that is the equation which we are going to use. So in this case, the change is 1.2, right? So percentage change is the changed value of 1.2 over the original value of 6 times 100. Perfect. So that becomes your changed value, which in this case will be, when you divide, this goes 0.2 times or 20%. Correct? So in this particular case, at the given point, the change is going to be 20% as shown here. So I hope this is understandable. Now let's go to question number 2. Question number 2 is find approximate value of cube root of 127, right? Since it is cube root, we'll take our function y as cube root of x, right? So dy dx for us will be equal to 1/3 of x to the power of 1 over 3 minus 1, which is 1/3 x to the power of minus 2 over 3. Correct? So that becomes your rate of change. So it will be 1 over 3 times, this could be written as square root, a cube root of x square. Correct? So that becomes dy by dx. Now if you look into the function, we could write this as, now we're looking for cube root. So 125 is exactly known to us as 5 and plus 2, right? That gives us 127 cube root. So in this case, what we really know here is that cube root of 125 is equal to 5 and the change which we are looking for, delta x, is 2. That is the value of delta x. Correct? So from here, we can always write that change in y is basically equal to 1 over 3 times 1 over cube root of x square times change in x. Correct? The approximation is because we are just taking this value, which is 2, which is not approaching, which is not very close to 0, right? So there is a huge change in the value. Correct? So that is how you get the changed value of y. So from here, you can actually substitute the value of x as 5. So in this case, delta x is 2, right? So, and we know the x value is 125, correct? So we can substitute this value to find change in y. So change in y basically will be equal to 1 over 3 times cube root of 125, its square, right? Times 2. So that gives you the change in the value of y, right? So which is basically 1 over 3, and this is 5 square, which is 25, times 2. Correct? So that is the changed value of which you can calculate as 2 over 75. Correct? So 2 over 75 is the changed value, and therefore you can now find the cube root of 127 as equal to sum of these two changed and the original value, which is 5, right? So it is 5 plus 2 over 75. Correct? Or you could write 5 2 over 75. You can use calculator to convert this to decimals, right? Or even you could divide and then figure it out. So it comes to 5.026, correct? So let's use calculator. You could actually times this if you don't want, if calculator is not allowed, right? If calculator is not allowed, in that case, what you should do is you should multiply this by 4, right? So if I do 4 times 4, you get 300 here. And then it becomes easy, right? So if you do 8 over 300, then you can get this decimal value. Is it okay? So let's calculate what is the cube root of 127 and how close are we. So we'll do shift cube root of 127, which is equal to how much? So the calculated value of cube root of 127 is actually equals to 5.0265, right? So as far as we are concerned, the value which we found up to the third decimal place was perfectly fine. Do you see that? So that is how you actually get your answer, right? So we know it is very close to 5, slightly away. That's the whole idea. Slightly away. And how much away? So we found the derivative of the function and multiplied by delta x, which was 2 for us, correct? So derivative into delta x gives us the answer. So always it could be any function. You can find 5th root, 6th root, whatever. Its derivative into delta x will be the change. So in short, the change in y value will be equal to f dash x times delta x, correct? And f dash x will be at a value which is known, f dash x at known value. So this is exact, is that okay? And then you multiply by delta x to get the value. Perfect. So I hope that aspect is very clear. Now let's take one more example, so I think you have understood the method. Once you have understood the method, see how easy it is and how much time do we take to calculate the approximate value using this method. In a multiple choice test paper also, you can actually find this answer in less than a minute, right? So we are given 3.968 to the power of 3 over 2, right? So that means our function y will be equal to x to the power of 3 over 2. Do you see that? X to the power of 3 over 2. So dy dx, differentiating, we get 3 over 2, x to the power of 3 over 2 minus 1. So which is dy dx. I'm taking extra steps. X to the power of 1 over 2, correct? So square root of x. Now, how can you approximate 3.968 to the power of 3 over 2? Well, the closest value is 4, right? So we could think that this value, 3.968, could be written as equal to 4 minus, so take away from 4 this value, so you get 0.032, right? So we could write this as, now this power to the power of 3 over 2 could be written like this, correct? So in our case, we will find rate of change at x equals to 4, correct? So we'll find now what is dy dx at x equal to 4. So we'll substitute 4 here. So we get 3 over 2 square root of 4, which is equal to 3. So that is the rate of change at this particular point, dy by dx. Now we need to approximate for this, right? Now from the derivative itself, we have got rate of change this. We can write dy is equal to 3 by 2 x to the power of half times change in x, correct? So I could have substituted here also. Let me substitute again now. 3 by 2 x is equal to 4 for us, right? So which is square root of 4 times the change here is 0.03832, right? This is the change, 0.032, correct? So the change in value is that much. This was a gradient at this point. Is that okay? So that becomes your change in y. So the change in y will be, this is 3 as you know, 3 times 0.032. So if you multiply, 3 times 2 is 6, 3 times 3 is 9, and then you get 0.0. So that is your change. Perfect? That is your change. Now, we should have found what is the value of 4 to the power of 3 over 2. Let's also calculate 4 to the power of 3 over 2. That is to say, square root of 4 and then cube, right? So it is kind of like this. 4 cube is okay. So square root of 4 and 2 cube is 8. So this is 8. And that is the change. And change we have to take away. Therefore, we can write our answer now. So what should be our answer? So I hope you got this. So we have 3.968 to the power of 3 by 2 should be equal to 8, and this was a negative change. This is minus, right? So let me make it very clear. So this is a negative change, so it is negative, or this value is negative, correct? So we'll from here take away 0.096. Do you see that? So it is slightly less than 8, and if you take away this, that is 4 less, right? So 7.904 will be your answer. Is it okay? So that is how you get your solution. 7.904. So this value is approximately equal to slightly less than 8, 7.904. Do you get an idea? So now let's check this value with calculator and see how close we are. 3.968 to the power of 3 divided by 2, right? That is equal to, so if you check your result, you actually get what? You actually get 7.904192. So if you compare up to 3 decimal places, we got an accurate answer. So this method is that simple. Basically, you have to get a perfect point here, which was 4 for us, and 4 to the power of 3 over 2 was 8. Delta x is minus, right? So we will write here, delta x for us is minus 0.032, and so the gradient multiplied with this minus gives us 0.096 negative value. Take away this value from 8 and get your answer. Do you see that? So only these 2 steps can actually give you the right answer to 3 decimal places. I hope you understand and appreciate it. Feel free to write your comments and share your views, and watch my detailed video on differentials, errors and approximations. You will come across many amazing examples which are going to help you in many test papers and also for entrance examinations to IITs. Thank you and all the best.